So welcome everybody to this week's or this day's Meow seminar, I should say, because we're having a Meow seminar also tomorrow, Tuesday. But today, Monday, we are hearing a talk by Christopher Hojny, who will tell us about proof logging for mixed integer programming. So Christopher, without further ado, please take it away.
Thanks, Jakob, for the introduction. And indeed, I want to talk about ways to certify reductions that happen within modern integer programming solvers, such that we can independently verify them to make sure that the results that we compute are actually correct. And everything that I want to talk about in the following is joint work together with my former PhD student Jasper von Dornmalen, Leon Eifler, and Ambrox Gleisner from Berlin. But before we actually jump right into the topic of this presentation, namely the proof logging, I first want to introduce the concept of mixed integer programming very, very briefly to make sure that everyone is on the same page. And in the following, when I refer to a mixed integer program, I'm always assuming that I have given a matrix A and two vectors B and C, such that I consider a system of linear inequalities encoded in this matrix vector inequality AX less than or equal B. And the goal of the mixed integer program is to find a vector X in which some of the coordinates are only allowed to take integer values that satisfies the system of linear inequalities. And among all these vectors, I'm looking for one that maximizes the objective function C transpose X. And let's try to visualize such a mixed integer program and some special cases, namely the first special case when the number of integer variables is 0. Then we are dealing with a so-called linear program, and the feasible region can be seen in this picture on the right-hand side here. It is just this blue region, which we call a polyhedron, and we're interested in some point in this blue region that maximizes this linear objective function. If some of the variables are supposed to take only integer values, then we're dealing with a mixed integer program. And in this case, not the entire blue region is the feasible region, but only some fibers along integer points, so the vertical dark blue lines. And in case that we're only interested in full integer solutions, so we don't have any continuous solutions at all, then we're interested in finding an integer vector inside this polyhedron that maximizes the objective function. So this is in a nutshell the framework of mixed integer programming, and it has become very, very popular since its innovation in the 1950s. It is used for many theoretical and real-world applications. And as you can imagine, it is used on a daily basis by many, many companies. But the problem is when these companies, for instance, solve their problems, they might not actually solve the problem. And there might be different reasons why, even though a MIP solver claims that it has solved a problem, it has in fact not solved the problem. The first could be because many, or almost all of the mixed integer programming solvers, they work with floating point arithmetic. So this means that the solutions that we compute might not actually satisfy all the inequalities in exact arithmetic. But, and if we abstract from this, there might also be a second source for mistakes or errors, namely that are bugs in our codes. So the solution that we compute is inherently wrong. And this can be very, very critical if we are really relying on finding true optimal solutions. So you might say, well, in an everyday's life situation, we might anyways not have perfect access to data. So also the data might be wrong in a certain sense. So maybe optimality or feasibility is actually not that much of an issue. But in some cases, it really matters. So for instance, suppose you want to prove a mathematical statement, and you want to do this by translating your mathematical problem in a mixed integer program, and then verifying that this MIP does not have a feasible solution. Then your code better should be correct, because otherwise the proof for the mathematical theorem that you provide is wrong. But there's of course also exist some practical applications, for instance, in the verification of computer chips, where you want to solve a mixed integer program to verify that the chip is functioning as expected, or also because of legal requirements, for instance, in the context of combinatorial auctions, you're required to find true optimal solutions. And the question in the following is, how can we achieve it that the solutions that we compute within a mixed integer programming solver are actually correct? And one solution would be to have a formally verified implementation of our mixed integer programming solver. One way of dealing with this is that we enumerate all the possible states that we can generate in the code, and then we need to verify that the reductions that we make within the code, so we train So we go from one state to another state in the code, that all these transitions are correct. While this is in principle possible, it's not very practical because the state space of a MIP solver is huge. So enumerating all the states can take a very long time if we're even able to enumerate all these states. And a second problem that arises here is that MIP solvers are continuously developed. So we do not have a static code base that we could verify once, and then we can make use of it also in the future. If we have every now and then a new feature, then we needed to re-verify the entire implementation again, which is of course also very impractical. For this reason, a different paradigm exists that says, well, maybe it's not necessary that we have a fully correct code as long as we can verify or certify that the result that we produce is actually correct. So this means if we take a look into this diagram, we start with our potentially erroneous code. So there might be some bugs in the code. We produce a solution along this lower connection, and then we accompany this solution with a proof of correctness. So for every step that we make in the code, we, for instance, write to a log file, a line that justifies why we made this reduction. And these reductions need to be, or these justifications need to be made very simple, such that an independent piece of software, a so-called proof checker, can verify that the reductions that we made are actually correct. And the good news about these proof checkers is that they are usually rather simple pieces of code, so they can actually be verified correctly, so we can guarantee that they work correctly. And with this, we at least do have some guarantees that the solutions that we produce are actually feasible and optimal to our problem. And this idea is also the basis for the work that I want to present in this presentation. And of course, this concept of proof logging is not new. It exists since at least 20 years in the SAT community. And whenever you now participate in a competition for SAT solving, you're also required to have such a proof that your result that you produce is actually correct. And these ideas have also been extended for pseudo-Boolean optimization a couple of years ago in a seminal paper by Bogarts and others, which will also be the basis for the work that I present in the following. And for MIP, there also exist some basic proof logging schemes that I will also discuss in a minute. And this brings me to the outline of this presentation. So first of all, before we can actually start certifying that the reductions that we make within a MIP solver are correct, we of course need to discuss what does it actually mean to solve a MIP, which techniques are used in practice. After that, I want to talk about this basic proof logging scheme for mixed integer programs called Viper. I want to discuss which basic reductions can be verified using this system, but where it also reaches its limitations. For instance, when it comes to more advanced MIP techniques that I want to discuss afterwards. And then to be able to at least guarantee certificates for these reductions in the context of pseudo-Boolean problems, I want to briefly explain the framework by Bogarts and others, which will then function as a bridge to our proof logging scheme that then also allows to certify reductions that we make in a mixed integer programming solver. So that's the outline of today. And let's start with the high-level ideas, how we actually solve mixed integer programs. And the basic idea of mixed integer programs is that we are relying on a tool that is called linear programming, which means we ignore all the integrality requirements and we solve our integer program as if there were no integer variables at all. So we insert an objective function that we want to maximize. So we want to maximize within the direction of this red arrow. And then we might find over this polyhedron, this red vertex at the top, which is an optimal solution of the linear programming problem. This solution, of course, does not satisfy the integrality requirements. And what then happens in practice is that one selects a variable which is not integer, and then one splits the problem into two subproblems and repeats this problem. And by this, we create a so-called branch and bound tree in which we repeatedly solve a sequence of linear programs until we find maybe in one subproblem an integer solution, which means that we now know at least some potentially suboptimal solution, but we can use this suboptimal solution to prune parts of the feasible region also in other subproblems that then cannot contain an improving solution. So if we now look into the subproblem that we've created on the right-hand side, we can discard everything that is below the red line. And then we iterate this procedure until we then eventually have eliminated all the subproblems from our region, and we have found an optimal integer solution if it exists. So that is the high-level idea that is behind all the mixed integer programming solvers that are used in practice. And what we can observe is that this plain idea actually is also the basic idea of the proof logging scheme that exists for MIPS, the so-called Viper proof system. And as we have seen in this branch and bound approach, that the core of solving mixed integer programs is solving linear programs. And the question is, so assuming that we do not have any integer variables at all, is it actually possible to provide a certificate for linear programs that we have found an optimal solution? And once we have established such a certificate, the question is, how can we embed such a certificate into a branch and bound solver? So let's consider an example to illustrate how certificates for linear programs work. We are given this toy example here, where we are given two variables, x and y, and we want to find a solution xy that satisfies these two constraints. So minus 5 times x plus y is at most minus 2, and 3 times x minus 2 times y is at most 1. And among all the solutions, we want to find one that minimizes the objective function 2x plus y. And I claim that the solution 3 over 7 and 1 over 7 is an optimal solution to this problem. And the question is, how can I actually convince you that this is an optimal solution? There's essentially two steps that I need to take. Namely, the first one is that I actually show that this is a feasible solution. This is rather easy. I just insert the solution x star y star into my inequality system, and I check that none of the constraints is violated. One can verify that this is indeed the case. And with this, I also know, if I evaluate the objective function, that the minimum objective value is at most 1. So I found a feasible solution which provides me an upper bound on the optimal objective value. And the next question is then, can I also find a lower bound that also takes value 1, such that I can convince myself that I indeed cannot find a solution that takes a value that is better than 1. And this might look challenging at first glance, but actually in this case, it is rather easy, because what I claim is I can just aggregate the inequalities of my optimization problem to derive a lower bound on the objective value. And by this aggregation step, I mean that I take these two inequalities, I just sum them up. If I do so, I end up in the inequality minus 2x minus y is at most minus 1. And if I bring everything on the other side, this inequality reads as 2x plus y is at most 1. And since these inequalities hold for every feasible solution, it in particular holds for an optimal solution. And for this reason, if I compare now this 2x plus y with my objective function, I see that any feasible solution satisfies that the objective value is at least 1. And combining this with a solution that achieves the value 1, I now know that x star y star indeed needs to be an optimal solution. You now might wonder, well, is it always that easy? And the duality theorem of linear programming tells us that it is essentially always as easy as on the previous slide. Namely, if I given a maximization problem that looks like this in this red box here, so we are maximizing a vector x that maximizes this objective function C transpose x, and it has to satisfy the inequality system ax at most b, then a solution x star is optimal if and only if it satisfies the linear inequality system, so it satisfies all the constraints, and I can find a non-negative multiplier for each of the constraints. If I collect these multipliers in a vector lambda, this just means I multiply it from the left-hand side with my inequality system. And then I need to be able to recover my objective function. So reweighting the inequalities with a non-negative multiplier and aggregating everything into a linear vector, This will result in the linear objective C. And I need to, I need to select the multipliers in such a way that if I also aggregate the weighted right-hand sides, I recover the objective value of the solution X star. And the duality of theory of linear programming tells me that such multipliers always exist. And in the following, I want to refer to such vector lambda as a dual certificate, because this arises from the so-called dual linear program. And of course, this statement does not only hold for problems in which an optimal solution exists. This statement can also be generalized to cases where we have an unbounded linear program, so there is no optimal solution because I can improve my objective arbitrarily. And it can also be defined for infeasible linear programs, so to certify that no solution exists at all. And the nice thing about these dual certificates is that many linear programming solvers automatically provide such certificates, for instance, if you solve it using the simplex algorithm. So now that we know how to certify optimality of solutions for linear programs, the question is, how can we embed this reasoning into a branch and bound solver? And to this end, I want to revisit what it actually means to have a branching decision. So for splitting a problem into two subproblems. What one then usually does is one selects a single variable, let's say xi, and creates two subproblems that arise by either enforcing that xi takes at most a value of gamma, which is an integer number, or xi is at least gamma plus 1. And this is a valid branching decision because I know that in between this interval, gamma and gamma plus 1, no feasible solution exists that satisfies that achieves a value in between these two numbers, because we are dealing with integer variables. And the idea of the Viper proof system is to incorporate such branching decisions into a certificate by so-called assumptions. So it says, let's assume that we have the additional property that xi is at most gamma, or let's assume that xi has the additional property that it's at least gamma plus 1. And if we then consider these two subproblems with these two different assumptions that we made, and we can prove that that both of them are infeasible, then we can also include, for instance, that if we remove these assumptions, that also the entire problem P that we started with is infeasible. Let's consider an example to illustrate this. So suppose I want to prove that for this toy example in the red box, x1 is at least 1, no matter which feasible solution I select. Then let's assume that the contrary was the case. So I add an assumption that xi is at most 0. Then I want to branch on the variable x2. And I also make here a case distinction by assuming that x2 is at most 0 or at least 1. If we are in the first case, then I can now take this duality reasoning with this dual certificate to prove that no feasible solution exists in which both x1 is at most 0 and x2 is at most 0. And I can do this by taking an aggregate of the constraints that exist in my system, in my original problem, and together with the assumptions that I made. And this then yields me the contradiction that 0 is at most 1. So I know that under the assumption A1, A2 cannot hold. Similarly, I can also argue for the case that x2 takes value at least 1. Then I find a different reweighting of the constraints and the assumptions, such that if I aggregate them, I again derive at a contradiction. And since both branches, x2 at most 0 and x2 at least 1, yielded a contradiction, I can conclude that whenever A1 holds, then I have an infeasible system. So I can show that in every feasible solution, we need to have x1 is at least 1. So this basic reasoning, so that we have optimality of linear programs and basic branching decisions, so vanilla branch and bound, this is actually supported by the Viper proof system. But it also reaches its limitations because in modern mixed integer programming solvers, more techniques exist. For instance, cutting planes. And a cutting plane is just a linear inequality, alpha transposed x at most beta, that is satisfied by all the mixed integer feasible solutions, but for which some points in the so-called LP relaxation in this blue polyhedron exists that is violated. So for instance, if I take this red point in the picture on the right-hand side, a cutting plane would be this red line because all the mixed integer feasible points are below the red line, but the red point violates this inequality. So I can add this inequality to my mixed integer program to reduce the feasible region without cutting off any solution that is feasible for the mixed integer program. But I will get rid of some LP solutions. The nice thing about these cutting planes is that they do not only serve as an additional tool, they can also be combined with branch and bound. So whenever I compute a solution of a linear program, I can also check whether there exists a violated inequality and I can add it. And this allows me to combine the, let's say, combinatorial ideas of branch and bound with more geometrically inspired ideas like these cutting planes. And there exists also a very basic family of cutting planes, so-called Châtal-Gomery cuts, which work in the context of pure integer programs, so where we do not have any integer variables at all, as follows. I need to be able to find again an aggregation vector lambda that I multiply with my inequality system. And if it happens that this aggregated inequality produces a vector C in which all the coordinates are integer, then I can derive a new inequality that for sure holds, namely by saying that C transposed X is at most delta. And if it happens that delta takes a non-integer value on the right-hand side, then I can also compute the floor value to strengthen this inequality. And this is indeed a valid approach because the vector C only has only integer coordinates. Every solution takes only integer values. So this number C transposed X on the left-hand side here is an integer number for every feasible solution. And this means that I can replace the right-hand side here by the floor value. So I can derive a stronger cutting plane than just aggregation. And this simple, let's say, rounding mechanism is also supported within Viper. So to summarize this, in Viper, we have the basic textbook branch and bound approach. We have these basic cutting planes from the previous slide, but there exist many, many more reductions that we can find in modern mixed integer programming solvers that are not expressible within the Viper system, at least not at the moment. For instance, specific pre-solving reductions, variable domain propagation, many, many more cutting planes, and symmetry handling. And of course, this is rather vague what I mentioned here because I haven't explained these concepts. But on the next slides, I also want to add a few more details about some of these techniques to illustrate why they are not supported by Viper. And to illustrate this, I want to consider this toy example of a mixed integer program, which contains 4 variables, x, y, z, and z prime. Z and Z prime, they are continuous variables, whereas X and Y, they are integer variables. And what happens actually in a mixed integer programming solver? It tries to simplify this problem because it's maybe too complicated, it has too many variables, and maybe there exist very cheap steps that we can execute to make the problem easier to solve such that we save a lot of time in branch and bound. And the first reduction that we could observe is that y is an integer variable, but this upper bound on y is a non-integer number. So what we can do is we can just replace this 6.5 by a 6, because we know that no feasible solution can have a value that is larger than 6. If we have improved this, we can also now look into these continuous variables z and z prime, and I claim that I can fix z prime to 0. And the reason for this is that if I look into the constraints here, then the coefficient in front of z prime is always larger than the coefficient in front of z. So this means if I take the value in a solution of z prime and I shift it to z, more formally, if I replace a solution z comma z prime just by z plus z prime comma 0, then I obtain a feasible solution because the constraint has more slack. So the possibly larger amount, 2 times z prime, is reduced to only z. The solution stays non-negative, because 0 is, of course, non-negative, and we had non-negative numbers beforehand. So z plus z prime is also non-negative. And the objective doesn't change, because it doesn't matter whether I insert z in this variable here and z prime here, or nothing in z prime, or the value of z plus z prime in the first variable. So the objective doesn't change. So this means I can take a feasible solution, manipulate it, and obtain another feasible solution that is not worse than the previous solution that I started with. And this is so-called dominated column pre-solving. And if I do this, my problem reduces to the following. I can save one variable. And if I now stare at the variables x and y, then I can observe that they behave symmetrically. So for instance, I can take a feasible solution x comma y, and I can just flip the meaning of x and y. And this will give me another feasible solution with the same objective value, because the objective is invariant under flipping x and y. And for the remaining constraints, I can observe that if I replace x by y, there's a symmetric constraint in which the other direction of this swap will happen. And this means in an optimal solution, I can also assume without loss of generality that x is not smaller than y, because otherwise I'll find just a symmetric solution in which I swap the meaning of the two variables. So these were three basic pre-solving reductions. And what we observed for these pre-solving reductions is, in principle, that there is a following fundamental difference. Namely, the first one, where I replaced the right-hand side of 6.5 by 6. This reduction did not remove any feasible solutions. So this variable bound tightening is in principle representable in Viper by using one of these rounding cutting planes, where I then just reduce the right-hand side. But what is in principle not supported is that I can remove the old constraint. So Viper also needs to detect that the previous constraint became redundant after adding this strengthened cut. And for the other two reductions, this dominated columns and the symmetry reductions, they are currently not representable within Viper because they remove feasible solutions. And this reasoning is currently not supported. And the question in the following is, how can we actually incorporate such reductions? How can we certify such reductions that also remove feasible solutions? And to illustrate this, to motivate how we can certify this, I want to now change the focus to a second proof system that has been introduced a couple of years ago by Bogarts and others for so-called pseudo-Boolean optimization problems. And these are, in a certain sense, special cases of mixed integer programs in which we assume that all the variables can only take binary values. And for notational convention, I assume in the following that we are dealing with greater than or equal constraints and that we are minimizing the objective. And we also assume in the following that all the data in A, B, and C are integer numbers. I further want to introduce the following two notations, which will make life a little bit easier when it comes to writing down formulas. By capital F, I want to denote the set of all the binary vectors that satisfy this inequality system. So this is the feasible region of my pseudo-Boolean optimization problem. And the objective function, this linear function C transposed X, I want to abbreviate in the following just by lowercase f. What is the high-level idea of this proof logging systems that Bogarts and others introduced? They use the so-called terminology of constraints, which is just the set of binary vectors that satisfy a single linear inequality. And their reasoning is based on defining two sets of constraints. The so-called core constraints, which I denote in the following by a curly C, and the derived constraints that I denote by a curly D. And you can think about these core constraints as the original constraints that define my pseudo-Boolean optimization problem, and the derived constraints, which can be thought of as the additional constraints that are derived while solving the problem. So for instance, this fixing a variable to 0 because of dominated columns, or x is at least as large as y if we're dealing with symmetry reduction. And the high-level idea is that I want to prove in the end that my problem becomes infeasible. Maybe I know that that a feasible solution exists with a specific objective value, and I want to prove that no better solution exists. So if I introduce an objective cutoff, then I want to prove that this restricted problem where I want to find an improving solution is infeasible. And this is then achieved in this proof system by proving that the empty set, so the constraint that has no feasible solution at all, is within my set of derived constraints. And if I can prove this, then indeed I know, because all the reductions that I made beforehand, they together imply that there is no feasible solution at all. I can conclude infeasibility of my original problem. But this is, of course, difficult, because proving that the empty set is a derived constraint is as difficult as solving the entire problem, because this is actually what we want to do. And so their idea is to start with a configuration C, D of core and derived constraints that is relatively easy. And then I want to gradually change it. And I want to prove that every of these changes that I apply is actually feasible. It's a valid change, such that in the end I can verify that the empty set is indeed in the set of the derived constraints. So let me, to this end, to be able to implement this mechanism, introduce the notion of a so-called configuration. And a configuration is a triple of two sets of constraints, C, D, so the core and the derived constraints, and an integer number, Z, or infinity, which can be thought of as an objective bound. So suppose I know a feasible solution, then Z can take the value of this feasible solution. And just to illustrate again these concept of constraints, let me just write down how such a set curly C could look like. It consists of, in this example here, of two constraints, and each of these constraints are all the binary vectors X that satisfy a given linear inequality. And for notational ease, I also want to introduce the notion, the intersection of curly C, so the intersection of all the core constraints, which means I take all the constraints that live inside this set curly C, and I compute their intersection. So it is the feasible region induced by all the constraints that are stored in this set of the core constraints. So all the binary vectors that satisfy all of these constraints simultaneously. And the idea of this proof system is then that we start with one such configuration that has some properties that I will want to explain in a minute. And then I want to change this configuration slightly, such that I can prove that in the end, the empty set is contained in the derived constraints. And of course, this means that I somehow need to link this configuration with the problem that I actually want to solve. And the first attempt that one might think of is then the following. I call such a configuration coupled to the problem that I want to solve, or f, valid, if it has three properties. The first property is that when this value z, which can be thought of as an upper bound on the best objective value, takes a finite value, then there also must exist a solution x in the feasible region of my optimization problem with an objective value that is not worse than this upper bound z. If I'm considering improving objective values, the second property says that I can find a vector x bar in the feasible set F with an objective value that is not worse than z prime, if and only if there's also a vector x that satisfies all the core constraints with an objective value that is not worse than z prime. So I have a translation, so to say, of the objective bounds from the problem that I actually want to solve and the constraints that are encoded in the core constraints. And the third property says that the derived constraints are not allowed to be too restrictive, meaning that when I take a feasible solution X that satisfies all the core constraints with an improving objective value f of x, then I also need to be able to find a solution Y that satisfies both the core and the derived constraints, and which also improves upon the objective value Z. So in this picture, this means I have the core constraints. I have derived some constraints, and as we can see, these derived constraints do not cover all the solutions that satisfy the core constraints. And then this property V3 tells me if there is a solution that only satisfies the core constraints, but not necessarily derived constraints, I need to find an alternative solution Y that satisfies both the core and the derived constraints, and which also improves upon the objective function of Z. In this definition, I called this configuration a first attempt because it is also not very strong, as we will see in a minute. But let me show you what we can actually achieve with such a basic version of a proof system. Namely, if we are given such a configuration C, D, Z, that is FF valid, and we assume that the empty set is within the set of derived constraints, then I can prove that there is no solution X in the feasible region capital F that improves upon the objective value Z. And this is in fact relatively easy. So suppose this was not the case. So there exists indeed a solution X bar in the feasible region that improves the objective. Then the property V2 tells me that there must also exist a vector X that satisfies all the core constraints and improves the objective. And by V3, I also know that there must exist a vector Y that improves upon the objective and that satisfies both the core and the derived constraints. But this is not possible because the empty set is within the set of derived constraints, so such a vector Y cannot exist. So for this reason, if I have an FF valid configuration and I can prove that the empty set is contained in the set of derived constraints, then I also know there is no solution with a better objective value than Z. And the idea of the proof system of Bogarts and others is then, okay, it is difficult to prove that the empty set is contained in the set of derived constraints, but let's start with an easy FF valid configuration for which I can easily prove that validity holds. And then I create a sequence of related configurations such that all of these transitions from configuration I to I+1 is easy. And if each of these steps is easy, then I can also in combination relatively easy prove that the empty set is contained in the derived constraints of the final configuration. As an initial configuration, we can then just take the feasible region F for which we want to solve the optimization problem. The derived constraints are empty because we haven't started solving the problem yet. And as an upper bound, we can just take infinity. And then it is easy to check that this satisfies the requirements of an FF valid configuration. And we can also prove very basic transition rules from one configuration to the other. For example, an objective bound update rule, which means, hey, I find a solution X that adheres to the core constraints. It improves upon the objective value by a better objective value Z prime. And then I can replace the old value of Z by this new value Z prime. So this is also a very, let's say, natural update rule. So whenever, for instance, in a mixed integer programming solver, I would find an improving solution, I, of course, would also update the best known objective value that I found so far. And we can also derive more interesting reductions, so implied constraints. So suppose I have a constraint C that I can derive from the core constraints, the derived constraints, and an objective improvement via a cutting plane that is also supported by Viper. Then I can add this new constraint also to the set of derived constraints. So these very simple transition rules can be implemented in this basic configuration setup, and they can also easily be checked by an automatic proof checker, but they are not very powerful yet. So because we have not discussed any reduction that we can use, for instance, for these dominated columns of symmetry reductions. And the reason is that it is intrinsic to this first definition of a configuration because it does not allow to prove these reductions in a very easy way. And the idea of Bogarts and others was then to enrich the definition of a configuration by a fourth item, namely a pre-order on the set of the binary vectors. So a binary relation that is both transitive and reflexive. And they suggest to slightly manipulate the definition of these three requirements namely in the last step, that when I'm looking for a solution that does not only satisfy the core constraints, but the core and derived constraints, that I then also need to make sure that this alternative solution Y improves upon X or does not get worse than X with respect to this pre-order. And pictorially speaking, this means if I start with my unordered set of core constraints and derived constraints, I now impose some more structure, and all the reductions that I make when going from a solution that only satisfies the core constraints to also a solution that satisfies the derived constraints, I'm not allowed to go left. I'm only allowed to either go upwards or to the right to satisfy this pre-order requirement. And making use of this pre-order then allows to indeed prove the reductions that I've shown before, this dominated column pre-solving and symmetry reductions. So for instance, here we have again a situation where we can fix variable x2 to 0 because we can just shift the contribution of x2 in the solution to the first coordinate. Of course, this is invariant under the constraint that we have here, and it improves upon the objective function. So we can fix the variable to the lower bound. And if we assume that this pre-order that we have selected in the configuration is the standard lexicographic comparison on the vector x1 and x2, then this change here that we shift the weight of x2 to the first coordinate also improves upon this lexicographic comparison. And this can be made formal, this map that translates the solution X into the solution Y. This can be made formal. So suppose we are dealing with a valid configuration, and we have a solution that satisfies the core and the derived constraints, but not necessarily a constraint that I would like to derive. Then there must exist a so-called witness omega that maps binary vectors onto binary vectors, and that has the following property, namely this manipulation omega of X needs to satisfy the core constraints, the derived constraints, and this newly derived constraint. In the example on the left-hand side, this means I satisfy all the constraints that I had before, but additionally, I also satisfy the constraint that I fixed the second variable to 0. And I need to do this in such a way that this witness does not get worse with respect to the pre-order, and it also does not get worse with respect to the objective function. And so this witness is an abstract description of this map that I have defined in the example on the left-hand side. And if and one can then prove, and a proof checker can then just verify that we are dealing with such a witness, that the witness is indeed these properties, and if it has these properties, then I can add this new constraint to the set of derived constraints. With a similar idea, one can also try to prove symmetry reductions via a so-called dominance-based strengthening rule. In this example, we can observe that x1 and x2 are both symmetric. So in every feasible solution, I can change the role of x1 and x2 when I don't change the objective function value, and I also don't change the feasibility. So this means I introduce a new solution that just flips these two variable entries. And if I again assume that the pre-order that I've selected is the lexicographic comparison, then I need to make sure that this flip, if it does not satisfy the constraint x1 greater than x2, then this flip will satisfy this constraint here, of course, and it will also improve with respect to the lexicographic comparison. And also this can be made more abstract. Also here we need to have an witness omega, such that if I are given a solution X that satisfies the core and the derived constraints, but that does not satisfy, for instance, this symmetry reduction, x1 greater than or equal x2, then the witness needs to satisfy the core constraints, not necessarily the derived constraints, only the core constraints. It needs to strictly improve upon this pre-order, so it's not allowed to stay at the same position, and we are not allowed to get worse than the objective function. And if the witness has these properties, then again, one can certify that this is a feasible reduction. And this will also be very important for our proof system that I will introduce afterwards, And I want to show you the proof idea, why this dominance-based strengthening rule actually works. So suppose we start with a solution here in this upper left corner of the red region that satisfies the core constraints and the derived constraints, but not necessarily the new reduction in this gray area on the right-hand side here. Then the dominance-based strengthening rule says that the witness omega needs to satisfy the core constraints, so it's contained in the blue region, and it strictly improves with respect to this pre-order on the solution that I had before. So I make a step to the right, and now I still don't satisfy the core constraints, the new constraint C, but I can iterate this scheme until I eventually hit a solution that does not satisfy the derived constraints anymore. But then I can use the property V3 from the certificate that says for every solution that satisfies the core constraints, I also find a solution that satisfies the core and the derived constraints, and which does not get worse with respect to the comparison, the pre-order. Now I'm back again in business. I can again apply the dominance-based strengthening rule, and now I find a solution that also satisfies these new gray constraints. So by a repeated application of dominance-based strengthening and the V3 rule, I can show that the new constraint that I want to derive holds. Now you might say, okay, in this picture, I just assume that I make a step upwards, but the dominance-based strengthening rule could also have said, well, we stay on the lower level, and then we now satisfy this new constraint C, but we don't satisfy the derived constraints anymore. So I've cheated maybe a bit, but this is indeed not the case, because now I can repeat this argument, and now I necessarily either have proven that my dominance-based strengthening witness doesn't work, because if I now make a step to the right-hand side, then I leave the core constraints. So my witness would tell me, okay, I cannot reach this step if I now need to go right. So I need to necessarily go up to satisfy both the core and the derived constraints and this new constraint C. And this repeated application of V3 and the dominance-based strengthening rule needs to necessarily terminate in finite time, because we are dealing with a pseudo-Boolean optimization problem. So we cannot create an infinite sequence of binary vectors that always improve with respect to this pre-order, but will never satisfy this new constraint that I want to derive. And these were the two main rules that also led us thinking about how can we actually generalize this framework of the pseudo-Boolean optimization world to general mixed integer programs, and in particular such that also further rules that they derive, for instance, we can delete certain core and derived constraints if they became redundant. How can we change derived constraints into core constraints? How can we change this pre-order maybe if it's easier for proving something? We were wondering, how can we actually generalize these techniques for general mixed integer programs? And this leads me to the definition now finally of the proof logging scheme that we propose for mixed integer programs. And as you will see, there are lots of similarities with this framework of Bogaerts and others, but there are some slight and subtle differences. And in the following, I want to talk about optimization problems in a very general language. So I assume that we are minimizing some objective function f, subject to x's contained in some reason, a feasible region f. And I again assume that this feasible region is defined by some sets of constraints. For instance, linear constraints, if you want, for the world of MIP. The configurations that we work with are more general, but they also contain core and derived constraints, which can be assumed to be some subsets of collections of the power set, so collections of constraint sets that are representable in the optimization problem that we want to work with. We are given some function g, which is not necessarily the original objective function. And we also have a placeholder value z for an upper bound on the optimal objective value. And we are dealing with a pair of orders, a pre-order and a strict order on Rn. And I want to stress that this strict order is not necessarily the strict order that is induced by the pre-order. It can be some other order. So that is not relevant for us. They can, in principle, be completely different as long as they certify some technical assumptions. And then I say that such a six-tuple of core constraints, derived constraints, a function g and value z, and these two orders is valid if it satisfies 5 properties. The first one we already know from the previous proof logging scheme. So whenever this value z is finite, then there must exist a feasible solution in the region F that has z as an upper bound on its objective value. Whenever we find, for no matter which new upper bound z prime might take, then there must exist a feasible. So whenever I find a feasible solution in the feasible region, which is not worse than this objective value z prime, then this is only allowed to be the case if and only if there exists a solution that satisfies the core constraints, and that is not worse than z prime with respect to this new function g. So you can think about this, for instance, as a manipulation of the objective function that arises when we are dealing with certain pre-solving reductions. We also copy-paste the requirement v3 from the previous proof logging scheme. So whenever we find a solution x that adheres to the core constraints and that improves upon the objective value z, then there must also exist a solution y that satisfies the core and the derived constraints. It improves upon the objective value and is not worse than the solution x that we started with respect to this pre-order. And now the two new assumptions enter the game. Namely, this pre-order and strict order, they are not allowed to be completely arbitrary. They must be linked, meaning that whenever I have that x2 is not worse than x1 in the pre-order and x3 is better than x2 in the strict order, then I also have kind of a transitivity between x1 and x3 in the strict order. So I need to be able to conclude that x1 is worse than x3 in the strict order. And this naturally holds if the strict order is the strict order that is induced by the pre-order. And as we have seen from the dominance-based strengthening rule, in the binary world, there cannot exist infinite sequences such that I can make arbitrarily in every step a progress. And this is a technical assumption that we need to introduce in our proof system. Namely, we assume that there is no infinite sequence inside the set of the core constraints, such that in every step I have a strict improvement with respect to this strict order, and I also do not get worse with respect to the objective function. And now you can see from this, hopefully from this pictorial proof of dominance-based strengthening, that with this technical assumption v4 and v5, we can also prove a version of dominance-based strengthening within this proof system for general optimization problems where we don't have the requirement that all the variables are binary. And
Can
what
I
we
just
then,
ask?
yes,
Sorry, so if you just go back, so just to understand, the G, we should think of this like intuitively, it's helpful to think of this as you manipulated the objective, maybe like you rewrote F to something else, but G is sort of the current representation of the objective. Is that the way to
yes,
think?
yes, this is how to think about it. So for instance, suppose we are dealing with the dominated columns, we fix a variable to 0, then we can also remove this variable from the objective, or ideally we can also remove the variable from the entire problem. And then technically it's not a function from Rn to R anymore, but from Rn minus 1 to R. So the function changed.
Okay, and the strict order, like one way of achieving V5 would be, for instance, that strict inequalities like by some constant additive difference, like
Exactly,
okay.
exactly. And this is also what we do in our realization that I talk about in 2 slides.
Okay, great, thanks.
Are there further questions? If that's not the case, so then let's continue. And what we prove in our preprint is that essentially all the rules that have been invented for this proof framework of Bogarts and others, they also carry over to our proof system. And as said before, so this assumption that there is no infinite sequence with strict progress allows us, for instance, to prove that the dominance-based strengthening rule also works within our setup. And when we apply this to the mixed integer programming world, then we can verify many, many different reductions. We can, for instance, still verify these cutting planes that were already existent in Viper, but we can also derive many more cutting planes from the family of disjunctive cuts, for instance, Schwartal-Gomery cuts, cover inequalities for knapsack problems, flow cover cuts. We can consider so-called extended formulations where we introduce new variables to be able to express certain inequalities in a nice way. We can use pre-solving reductions like reduced cost fixing and dominated columns. And to be able to do so, we need to derive a pair of orders of this pre-order and the strict order that can be used, for instance, for this dominance-based strengthening and redundancy-based strengthening. And ideally, we should design these orders in such a way that also symmetry handling techniques can be verified. And we demonstrate a way of deriving these rules for deriving or for certifying the reductions made by lexicographic order-based reductions, the so-called Schreier-Sims inequalities that we've also seen before, where we say that one variable xi takes at least the value of another variable xj, or the popular symmetry handling method, orbital branching, which is a branching rule that is based on symmetry information. To give you an idea how this works, I do not want to go into all the technical details. This is maybe something for the second part of the talk. But the idea is that we take the branching decisions, and based on the branching decisions, we define for every node in the branch and bound tree its own lexicographic order. But the lexicographic order not on the full variable space, but only the variables that we have seen while branching from the root node to, for instance, this red node here. And we would then sort the variables according to the branching decision. So we would say x4 is the most important variable, x2 is the second most important variable, which is followed by x1. And then the lexicographic order that we then, or the partial lexicographic order that we would then define at this red node, is the classical lexicographic order restricted to these three variables in the order 4 to 1. And why are we doing this? We're doing this because one can prove, we did this in earlier work, that if we use these, let's say, node individual lexicographic orders, we can show that most of the symmetry handling techniques that are used throughout integer programming solvers are actually derivable from lexicographic order constraints that follow this pattern. So for instance, this orbital branching and lexicographic order-based inequalities, isomorphism pruning, they can be derived from such a scheme. So we have now defined these lexicographic orders at nodes of the branch and bound tree, but in our configuration scheme, we need a single a single pre-order and a single strict order, not for every node of this tree, in particular because we don't know this tree in the configuration. And we've therefore introduced a new pair of strict orders and pre-orders on the entire variable space as follows. We define a tree that tries to resemble the branch and bound tree, but it can be also completely unrelated to the branch and bound tree. And then again, we derive for every node of this tree that we define a strict order, a strict partial order, as done on the previous slide. And to turn this into an order on the entire solution space, we compare two solutions x and y by checking at which leaves of this branch and bound tree-like tree are they feasible, and then we compare the two solutions x and y at the deepest common node. So at the deepest node in the branch and bound tree, where both of these solutions x and y were for the last time feasible. Afterwards, their paths diverge. And then we compare these two solutions, x and y, based on the strict order that we defined at the blue node. And we also derive a pre-order that is satisfied either if x is strictly greater than y at this node of the branch and bound tree, or they are the same. And as Jakob already pointed out, we achieve this by using this lexicographic order, this partial lexicographic order that I defined before here. But instead of requiring that the difference can be arbitrarily small, we require that if there is a difference in the first position where they differ, then this must be at least some epsilon value, such that we can make some strict progress, which will allow us, in the case of bounded variables, that there cannot be an infinite sequence. The technical difficulties, of course, are in this situation. How do we actually define such a tree, such it is not linked to the branch and bound tree that we use when solving the problem, such that we can define this in a very clean way? And in particular, how do we deal with continuous variables? Because there, this epsilon actually might make a difference. So to summarize this, we have provided a rather simple framework for certifying many popular MIP reductions. It's highly inspired by the framework of Bogarts and others. And for the first time, we can also make use of this framework to certify symmetry handling methods that act on non-binary variables. And apart from the rules that I've presented in this presentation, we have way more rules. We can, for instance, update the objective function. We can transfer constraints from the derived constraints to the core constraints, and so on and so forth. In practice, when we make use of this scheme, we, of course, are relating these trees that I defined on the previous slide to the branch and bound tree. But the question is it also possible because the framework is phrased in a very generic language, it's just a pair of a pre-order and a strict order, is it also possible to make use of this framework if we are not relying on such tree-based orders? And of course, from a practical perspective, it would be very interesting to implement this also in actual MIP software, such that we can be sure that the solutions that we produce are actually optimal solutions of our optimization problem. Thank you for your attention, and I'm happy to take your questions.
Thanks a lot, Christopher. Giving a round of applause on behalf of all of the audience. So the floor is now open for questions. Well, people, thank you. So this concept of orders seems more complicated now. Is part of it that I mean, from a solver point of view, do you generate this order? You generate it dynamically during search. Like if I forced
Yes.
to write it down at the beginning, you would have no clue.
This is in
Well, that's
principle
some clue.
possible. So what one can do is one can implement this either dynamically or statically. So statically meaning, for instance, I fix one order up front for all the nodes. Let's say it's the standard lexicographic order, and this is actually also how symmetry handling in the mixed integer programming literature started. But one observed that many of these techniques this can be relatively bad, because if I make a branching decision, let's say on the last variable, then this has no implications on my lexicographic order. For this reason, one has changed to a more dynamic framework, and in particular reductions that are derivable from these dynamically created orders that I sketched before. But in principle, the framework is also capable of dealing with static orders.
Yeah, but it's important that you're able to deal with dynamic orders.
Yes, because otherwise we are not able to certify some symmetry reductions like orbital branching.
And how do you, in a MIP setting, can I think of these order? I mean, I guess in the pseudo-Boolean setting, we just think of the order as being another pseudo-Boolean formula.
Mm-hmm.
But here, it's not like, could you think of the order as it would be some kind of mixed integer program of reasonable size, or no, not really? Will it be like, will it
Um,
have to be like a, by its nature, a different beast?
it depends a little bit. So if we are dealing with pure integer programs and all the variables are binary, sorry, not binary, integer, then I can write down the lexicographic order constraint as a linear inequality with very, very large coefficients. So for instance,
This
if
is
all the var
assuming bounded variables.
bounded variables, yes.
Mhm.
If I have an unbounded problem or problems with continuous variables, then the situation is different. Then I cannot write down a single linear inequality. And if I were to use, and if I do this for continuous problems, then the difficulty is also that the feasible region is no longer closed. And then it's also not representable in the mixed integer programming setup, because there I assume that I have greater than or equal or less than or equal constraints, but no strict comparisons. So I cannot model open sets.
Thank you. More questions from the audience?
I was wondering about the order in the symmetry breaking, because you said you have your tree and then you generate the lexicographical order essentially over this tree. Yeah, this slide. Um, but I'm wondering, then you have this order, and then maybe later you want to break a related symmetry that also includes some of these variables, but also some other variables. And then if you already have this symmetry breaking constraint in your core set, which would have to do if you switch orders, then you might not be able to break the symmetry anymore. So how can you sort of if you're breaking many symmetries, then how does it work in this case that you're committing to a relatively small order?
So this works because the reductions are only locally valid. So I do not add them to the entire problem, but suppose I'm at this red node, then I only impose the symmetry reductions at the red node or its successors. But I will not carry it over to, let's say, the node here on the right-hand side.
Okay, and then in practice, you would just delete those constraints once you have handled that node.
Exactly. Yes. Yes.
Or view them as, I guess we never promised that constraints would be linear inequalities, right? So here you would you have like some kind of activation variable that tells you that if you are in consistent with this node, then the following symmetry breaking constraints apply, something like
So
this?
what we do in practice, so if we have inequalities, they will usually be separated, meaning they enter a pool, they are locally valid, and when we go to another node, then we forget about these inequalities. Um, there exist some approaches where people actually added new binary variables to indicate whether one is at a specific node of the branch and bound tree to enable or disable these inequalities. And where we also don't need this is for propagation-based approaches, because there we do not add constraints, we just fix variables, or we improve bounds of variables. And this is then stored in the information of the node, so we can remember the reductions that we make. But of course, we needed to recompute the branching history then.
But from I mean, the proof doesn't have a concept of nodes and branches, or does it?
Yes, yes. So from a proof perspective, one would add a local constraint saying if the following variable bounds are satisfied, then this implies the following constraint is valid.
So any other question before we take a break? So then perhaps I would suggest that we take a break, but first we thank Christopher again. Thank you so much for the
Thank you.
presentation. So we are back after the break for the second half, the more technical half of the talk, and it's over to Christopher again, please.
Okay, thank you. So, as promised, now the more technical part where I want to go a little bit further into the details of the symmetry handling framework, the proof system, and how we actually encode these pairs of orders. But before going into these pairs of orders, let me maybe briefly talk about the symmetry handling framework, that it also becomes a bit more apparent why we actually use the definition of the orders as we did it. And the symmetries that I want to talk about in the following, they are permutation symmetries. And before defining these permutation symmetries, let me quickly say what in the following a general symmetry of a mixed integer program is. We can think about such a symmetry just as a map phi that maps from Rn to itself, such that whenever I take a vector x in Rn, then the solution phi of x needs to be feasible if and only if the solution that I started with was feasible. So the map phi preserves feasibility, and it's a symmetry, then it also should preserve the objective value. So the objective value of x needs to be the same as of the manipulated solution phi of x. And this notion of symmetries is, of course, very general, and a permutation symmetry is a very special case of such a symmetry. Namely, it's just represented by a permutation pi of the variable index set 1 to n. And then we define a new solution pi of x by permuting the indices of the corresponding solution vector. So we reshuffle the entries of the vector. And if this reshuffled vector satisfies the properties of a symmetry defined above, then we call pi a permutation symmetry of this problem. This is still a rather generic way of defining it, because if we stare into these two defining properties of a symmetry, in particular the first one, then we say that phi should preserve the feasibility of a solution. This is in general not very easy to inspect or to detect in general, because we do not know the set of feasible solutions explicitly. And for this reason, also in the setup of automatic proof logging, we will consider so-called formulation symmetries, which is a subset of the symmetries that keep the representation of the problem invariant. So this means we are again dealing with the permutation pi of the variable indices, but now we also need a permutation rho of the row index set 1 till m. And we say then that such a permutation pi is a formulation symmetry if it satisfies that it keeps the objective coefficient vector C invariant, and there must exist a permutation of the rows such that the row permutation keeps the right-hand side vector invariant. And if I manipulate the variables and the rows according to pi and rho, then also the matrix A needs to remain invariant. And then this is something that I can use, for instance, in dominance-based strengthening in an automatic proof checker. I can verify that a permutation pi is a formulation symmetry by providing the permutation pi along with its row permutation rho. So this is something that I then can also use in an automatic proof checker to see whether the proof that we've produced is actually correct. And to motivate the symmetry, the pre-order and the strict order that I've already sketched in the main presentation, let me go a little bit into the history of symmetry handling and how some symmetry handling techniques have been derived to illustrate why we opted for this definition of the orders based on the branch and boundary. And to this, for deriving this, I also want to introduce some additional notation with n in between these brackets. For the sake of convenience, I want to denote the first n natural numbers. And the symmetric group of this set is in the following, denoted by Sn, so all the permutations of the set of the first n natural numbers. In the following, when you will see a capital gamma, this will always correspond to a symmetry group of my mixed integer program. If I take a variable index I, then its orbit is given by all the possible images with respect to permutations in the symmetry group gamma. So I take my variable index I apply all the possible permutations that I have in my group to I, and then I collect the images j that I can find this way. If I given a single variable I, then the pointwise stabilizer with respect to this group gamma is given by all the permutations that do not move this ith element, and the setwise stabilizer for set A is defined similarly. Now I want that the image of elements from the set A are also mapped to elements within the set A. And the name stabilizer just means these elements or sets, they remain invariant under this subgroup, the stabilizer subgroup. If we start with one of the first generic symmetry handling methods that have been introduced now almost 25 years ago in integer programming, isomorphism pruning, the initial assumption was that all the variables that we are dealing with, they are binary, and that we use a lexicographic branching rule. That is, if I'm at the root node, no matter what the LP relaxation tells me, I always branch on variable x1. I go to the next level of the branch and bound tree. I will, no matter what the LP solution says, I will always branch on x2 and so forth. So at a node of depth d, I will branch on variable d plus 1. And what Margot back then introduced for isomorphism pruning was the idea that at a node of the branch and bound tree, when I use this branching rule, I collect the variables that have been branched to 1. So for instance, the node here at the lower end of the red path, if we check the branching decisions, then we have branched on variable 1 and 3. We have branched them to 1. And Margot proposed that we can prune a node of the branch and bound tree if the set of branching decisions B1 is not lexicographically minimal in its gamma orbit with respect to this group gamma. So this means if there was a permutation such that 1, 3 is, for instance, mapped to 1, 2, then I would prune this node of the branch and bound tree. And the idea is that I find lexicographically better solutions in a symmetric branch. This is, of course, a very restrictive setup of branch and bound because I'm severely limited on the branching decisions. So I have agreed on the branching decisions before I actually know which problem I want to solve. And for this reason, a couple of years later, Jim Ostrowski generalized this idea to arbitrary branching rules, and it comes back to the idea that I've already sketched in the main talk. Namely, we collect the branching decisions again to reach a specific node, and I define lexicographic order based on the variables that I've seen along the path on which I've branched. And then again, I prune a node if this set of branching decisions, the one branching decisions, is not the lexicographically minimal element now in a conjugated symmetry group with respect to a reordering of the branching variables. But the idea is in principle the same. It only allows me that I have a more flexible way of defining these orders. So instead of agreeing upfront on a lexicographic order, we now can have different lexicographic orders throughout the branch and bound tree, which allows to derive potentially more symmetry reductions. And this is the general paradigm for many symmetry handling techniques. So there's a static variant in which we fix a global lexicographic order up front, or we derive dynamically during the solving process a lexicographic order for the different nodes of the branch and bound tree, ideally from the branching history to ensure some compatibility between the lexicographic orders at the different nodes. And then I want to ideally prune nodes if I can detect that they do not contain any lexicographically maximal elements, which is unfortunately NP-hard in general. And if this is not possible or easily detectable for the problem that we want to solve, then we want to derive further symmetry reductions to at least partially handle symmetries. But most of the techniques that we see in the literature, they either use this global lexicographic order idea or the dynamically generated lexicographic order as depicted on the previous slide.
I didn't quite get the role of pi or how, but I don't know. Is this important to understand for the...
This is a technical way of writing down that when we compare two solutions, we do not consider the standard lexicographic order, but we would compare entry. So in this example here, we would take the subvector consisting of the entries x2, x7, and x3, and then compare it with its image with respect to this lexicographic order. This is a technical way of writing this down. This pi is this permutation that maps the first variable to 2, the second variable to 7, the seventh variable to, the second variable to position 1, the seventh variable to position 2, and the third variable on position 3.
Okay, so pi is not at all a symmetry of the input or anything like this.
No.
This is just okay, thanks.
It is just to formally define this restricted lexicographic order by reshuffling some of the entries. But you can just think about it, the order in which I've branched on the variables.
I see. Thanks.
Okay. So, and this idea of dynamically deriving the orders based on the branch and bound tree led us to the following idea to derive orders. And we wanted to be flexible, such that we do not want to restrict ourselves to always follow the branch and bound tree. And for this reason, we introduced a abstract generalization of branch and bound trees, which we call partition trees. And a partition tree consists of 6 elements, a set V and a set E, which define a finite rooted arborescence. And this R is then the root node of this arborescence. So you can think about it if you want. As the branch and bound tree that we create, R is the root node of the branch and bound tree. And when we split it, we add 2 child nodes to this arborescence, which models the respective child problems of the problem that we've just split. But in principle, this arborescence is unrelated to the branch and bound tree. Then we have a collection of sets B, which assign every node of this arborescence a subset of Rn. You can think about it if you want again to relate it with the branch and bound algorithm. You can think about this BV as the branching decisions that are, or the feasible region induced by the branching decisions that I've made to reach this node of the tree. So for instance, if I take the lower end of this red path, then this BV is all the vectors in Rn such that x2 is fixed to 1, x7 is fixed to 0, and x3 is fixed to 1. If you want to relate this to branch and bound, but in principle, these sets can be arbitrary. And then to generalize this notion of the restricted lexicographic orders, the final 2 ingredients of a partition tree is for every node of this tree an integer between 0 and n, and a bijection that maps the set 1 till mv, this number that we have selected beforehand, into a subset of the set 1 till n, and the cardinality of this subset is mv. So if you think about it again, this is exactly an abstract notion of defining these partial lexicographic orders from the previous slide. We just select a number of variables, mv, and then we select some mv numbers from the set of all the variables that we put into some order, and then we want to compare these, and this will define my partial lexicographic order. So this is an abstract generalization of these ingredients that we need in branch and bound. So these are this arborescence, which resembles the branch and bound tree, together with the feasible regions BV, and then this M and the sigma, they will be used to define some lexicographic comparison on a subset of the variables. Now, of course, this is not really what branch and bound does, because here we did not have any relations between these sets BV, so they can be arbitrary subsets. There's also no link between the M values and the sigmas, Whereas if we are in the situation of symmetry handling, the sigmas are not chosen arbitrarily. They are based on the branching decisions. So we also introduced different properties of a partition trees that we then use to define a so-called orderable partition tree. So we say that a partition tree is orderable if it satisfies four properties, namely that these sets BV are not allowed to be fully arbitrary. Whenever I take a node of my arborescence that has child nodes, so for which we have children, so the set of children is non-empty, then we need that the union of the sets that are assigned to the child nodes covers the feasible region at the parent node U. So this means, if you think about the branch and bound setting, we start with the parent node, we look into the children, we are not allowed to lose feasible solutions. But this requirement here says in principle that we can also have more solutions. Then, of course, in a true branch and bound tree, you would not want that you have solutions feasible at multiple of the children. And for this reason, we say that this map sigma, so if we apply this reshuffling of the solution space, if we apply it to the child nodes of a node U, then these reshuffled subvectors, they must be disjoint. So this means, let's forget about this sigma maybe first. If I take the feasible regions at two child nodes, then they are not allowed to overlap, which is exactly what happens in branch and bound. So we split the problem into two subproblems. And with, again, this map sigma U, we also allow for some reshuffling and only to focus on some part of the feasible region. So that we, for instance, get rid of some parts of the solution vectors if they are not relevant for us. Then we also need some requirements on these numbers M and on the maps sigma. We need that these M numbers grow if we go deeper down the tree. So if you think about these branching decisions, if we have a lexicographic order which is based on the branching decisions, then we must not forget something that we have done in the past. So the lexicographic orders that we grow along such a path, they indeed need to grow. So we are not allowed to remove information. And this is also captured by this second notion here, this notation, that if we have the map sigma at a parent node and at a child node, then all the information that was present at the parent node needs also to be present at the child node. So we are not allowed to arbitrarily change our lexicographic orders. In a certain way, this says we are only allowed to extend them. And a technical assumption that we need for proving symmetry reductions is that if we are considering the variables with indices in sigma v of I, then these variables need to be bounded from below. So we are allowed to, so it's not possible that we have completely free variables. And this is a technical assumption that we also need then for proving that there cannot exist infinite sequences that we have in our dominance-based strengthening rule. We need some kind of boundedness such that we cannot go arbitrarily far. And then we say that such an ordered partition tree or orderable partition tree is consistent with a set of core constraints if the feasible region BR at the root node contains all the elements from the core constraints. So we also need to link this somehow to the problem that we would like to solve. So we could, for instance, say that BR is the set of all the mixed integer points that satisfy the constraints that define my mixed integer program. Other questions so far? So if that's not the case, then we can now define our tree-based orders that make use of these consistent orderable partition trees. And here we introduce this epsilon that we also mentioned in the main talk. And we assume that we are given a positive integer number. And then we introduce a strict lexicographic order or lexicographic order with tolerances by saying that x and y, if these are vectors in Rn, then they satisfy this binary relation x epsilon greater than v, if and only if there exists an index k in, and this should be an n, not an m, such that on the first k minus 1 entries, these two vectors are identical, but in the kth position, x is at least by epsilon larger than y. So it's in principle like a lexicographic order, but we here require that if the vectors differ in the first position where they differ, they need to differ by at least an amount of epsilon.
And this is important that in the first they're exactly equal and then they differ by a noticeable amount.
Yes.
This is important for soundness of, okay.
This is important for proving that there cannot exist infinite sequences. Because this will guarantee us in the proof of the dominance-based strengthening rule, or for proving that there cannot exist infinite sequences within the core constraints. This will prove us, so if we have this boundedness assumption that at least they are bounded in one direction, that if we make a strict improvement step with respect to such an order, then we make an improvement step by at least epsilon. And this means after finitely many iterations, we need to hit this boundary of the partially or of the semi-bounded region, so that we cannot have arbitrary growth, so to say.
Yeah, I was just thinking, but probably there's an easy example where this fails. You could imagine that they're roughly equal up until the point where they're clearly apart, rather than exactly equal until they're not equal. But then probably this small, non-noticeable differences could accumulate in weird directions and make weird things happen.
Yeah. And after introducing this notion of the lexicographic order with tolerances, we can then define, as already depicted in the main presentation, our tree-based orders. So we take an ordered partition tree or an orderable partition tree that is consistent. We have this value of epsilon. And when we want to compare two solutions x and y that are feasible at the root node, so that are feasible for our problem that we want to solve, then we check at which nodes of this partition tree are these two solutions x and y feasible, by the assumption that the partition tree is orderable. We have that there is exactly one of the leaf nodes that satisfies one of these solutions. And then we check, okay, what is their deepest common node or their first common ancestor, u, in this example here. And then we use this strict lexicographic comparison at node u, which is defined by these maps sigma u that we defined on the previous slides. And if you want to think less abstract about this, this is just the lexicographic order derived from the branching decisions to reach the node u. And then we make an epsilon comparison there. So this is how we define the strict order. And the pre-order is defined by replacing this strict lexicographic comparison by a weak lexicographic comparison, which is essentially saying we are weakly epsilon lexicographic comparable if we are either strict comparable or the two vectors are the same. And this is how we define these tree orders. And of course, you might wonder, we have now fixed, for instance, this value of epsilon. Isn't this something that can hurt? Maybe for deriving specific reductions, we needed smaller values of epsilon. This is not a problem because for this realization of this abstract framework that I talked about in the main presentation, we also have specialized transition rules that allow us to go from one configuration to another configuration. For instance, one can prove that one can make epsilon smaller. We can also replace the entire order in a certain sense. If we first remove all the, if we first move all the derived constraints to the core constraints, then we can remove the tree that we have started with. We can replace it by a completely other orderable partition tree, and then start, let's say, anew with the orders derived from this different tree. So you can envision this as a restart. We have derived new constraints. Let's move this to the core constraints to define a completely new problem, and then start solving this problem from scratch. And if you don't want to do this, you want to continue solving your problem, and you want to derive these orders as we also would do it within branch and bound. So we want to derive them dynamically. Then we also have a tree refinement rule that says if we take our tree, we take a leaf node, we branch upon it, then we can refine the orders that we have used beforehand by the orders for this refined tree. And this also carries over such that we do not need to solve our problem at first completely to derive the final branch and bound tree, and then deriving from this the tree-based order. No, we can also do this dynamically by refining the rules, by refining the tree during solving the problem. And if there's interest, I can also talk a little bit about symmetry handling methods and how we can actually verify or certify these methods within this proof system.
Yes.
Okay. So recall maybe that for defining this, or for that I told you in the beginning of this second part, that many of the symmetry reductions that are actually discussed in the literature can be derived from such a dynamic lexicographic comparison. A rule where we define these lexicographic orders dynamically based on the branching history. So the core is that we somehow need to be able to also derive these lexicographic order constraints within our proof system. And to do this, let's recall how we defined this strict epsilon lexicographic comparison. So on the first k minus 1 positions, there must exist an index k such that on the first k minus 1 positions, the two solutions are the same. And in the kth position, they differ by at least epsilon. And what we then can do is we can use the dominance-based strengthening rule to derive at every node of the branch and bound tree for a formulation symmetry gamma that the following constraint that says if we are feasible at the node V of the branch and bound tree, and with respect to this local adapted lexicographic order where we reshuffled the variables, we agree on the first k minus 1 entries, then we can use the lexicographic, the dominance-based strengthening rule to derive that under the assumption here on the left-hand side, I can satisfy the following constraint, namely that, and here's an index k missing, that the kth position of the reshuffled vector x is at least as large as the kth entry of gamma of x minus epsilon. So it is not exactly what you wanted to have for the classical lexicographic order, where you wanted that x is greater than or equal gamma of x, but we need to weaken this inequality a bit, and we need to reduce the right-hand side by minus epsilon. And for continuous variables, this is the best that we can do. And for integer variables, we can then use, for instance, Viper cutting planes to round the right-hand side such that we also get rid of the epsilon if it's between 0 and 1. So dominance-based strengthening can be used to translate, to derive this, in principle, prose description of the epsilon comparison if we weaken it a little bit. So instead of plus epsilon, we need a minus epsilon here.
So
And
one thing I didn't understand, like, are you fixing K or?
no, I'm not fixing K. I'm just saying there exists a K.
Yeah, but in the actual constraint and the bottom of the slide.
Yes. So here I fix it. Here I fix it.
Okay.
But then maybe, for instance, or suppose I have a very large K that I have. It's not that I derive this constraint for a single value of K. I derive it for all the possible values of K. And then I need to check, okay, to which of these conditions on the left-hand side do I adhere? So which of these constraints is actually locally valid?
But this constraint, like if they would happen to be equal in position K, this constraint still remains valid.
It still remains valid, exactly, because we have the
Okay.
minus epsilon here. And
Right.
then I can
Okay.
continue with a constraint for K plus 1, for K plus 2, and so forth.
Okay, I see. So, okay.
And with this basic setup here, we can derive some symmetry handling inequalities, for instance, SST cuts. And an SST cut is in principle a generalization of the following type of constraints. So assume for the sake of simplicity that we use the standard lexicographic order for our comparison. And then we can say that if we consider the variable orbit of the first variable x1, then x1 shall take the largest value that we can find within this orbit. So we can say that x1 is greater than or equal than xj for all the variables that are symmetric to x1. And this is a standard inequality that is used in the mixed integer programming literature, but it's relatively weak because it only considers the variables of the orbit of x1. And one can generalize this to also further orbits if one replaces the gamma orbit by a suitable stabilizer subgroup of the entire group. So suppose I have added these inequalities. X1 is greater than or equal to everything in its orbit. Suppose I have added these inequalities, then I can reintroduce these inequalities for X2 if I replace the group gamma by the group consisting of all the permutations that fix element X1. Because then, if I derive these new constraints, I cannot violate one of the previous inequalities because X1 is fixed, so the largest element remains at its position, and then I can reiterate this scheme. And these inequalities do not only apply to binary variables, they apply to arbitrary variables, so in particular unbounded integer variables and continuous variables. And we can use these abstract constraints from the previous slide to derive these inequalities. We can, at least in a weaker form, we can then derive the inequality that xi is greater than or equal xj minus epsilon from the lexicographic constraint from the previous slide. And if the variable turns out to be integer, then I can also get rid of the epsilon on the right-hand side by a rounding argument that I then can use by a Viper cutting plane, for instance. Orbital fixing is another technique that is discussed. And for the sake of simplicity, let's assume that all the variables are binary. So we then follow again a path in the branch and bound tree. We collect all the variables that have been branched to 1. And then we compute the stabilizer group of this set. So we consider all the variables. So we are only considering permutations that map variables that have been branched to 1 to potentially other variables that have been branched to 1. This is a subgroup of the original symmetry group. And then the orbital fixing rule says, if there exists a variable that is fixed to 0, maybe not necessarily due to branching, Then I compute with respect to this stabilizer subgroup the orbit of this variable, and I can fix every variable inside this orbit to 0, and similarly for variables that are fixed to 1. And because we have proven in a different paper that these reductions can be derived from a lexicographic order constraint, a dynamic lexicographic order constraint, we can also use these epsilon lexicographic order constraints that are derivable via dominance-based strengthening. We can also use them to certify the reductions by orbital fixing. And of course, we can also derive reductions within the proof logging scheme that are based on a classical lexicographic comparison. So for instance, if we have two partially filled binary vectors, partial because for branching decisions, so we have branched some variables, for instance, to 0 and 1, and we want to enforce by symmetry handling that x is lexicographically not smaller than the second column, gamma of x, then we can just use these epsilon lexicographic comparison constraints that were derivable by dominance-based strengthening to see that the first entry on the right-hand side needs to be 0, because otherwise we violate this constraint, because x, or the entry on the left-hand side, needs to be at least as large as the entry on the right-hand side minus epsilon. And since we have a 0 here, and we have a binary domain here on the other side, we can then use this constraint together with, for instance, the Viper cutting plane to prove that we also need to satisfy that this entry here gets value 0. Similarly, we can do this to find that we also need to have a value of 1 here. If we take the k value of 2 for this lexicographic comparison constraint, now we reach, for instance, this position. Here we have two different choices. We see that if we fix this entry to be 1, then for sure the lexicographic comparison holds. The question would be, is it also possible that this is a 0? Following the Viper framework, we could just say, okay, let's assume that this entry was 0, and let's continue with the propagation. Then we would find that this entry here must be 0 because of the lexicographic comparison. And in the last row, we now see that we have created a vector such that the left column is lexicographically strictly smaller than the right column. So we violate the lexicographic order constraint. And for this reason, our assumptions must be wrong, and we can fix this entry here to 1. And these are all reductions that can be derived from these simple constraints that we can derive via dominance-based strengthening. And this was a high-level overview of the symmetry handling techniques that we can verify in this proof system. And that were all the slides that I had prepared.
Thanks a lot. So one of these, what was it called? The orbital fixing, the one where you had fixed things to 0.
Yes.
Are those actually given the current set of constraints? These are actually slightly different in that they're actually implied. Is that correct? I mean, these zeros, because you could say like there is some way that I derive the first guy to be 0.
Mm-hmm.
And now if I would just apply symmetries on the whole derivation up to this point, then I would actually get proofs that the other, not that they're 0 without loss of generality, but they actually have to be 0.
Yes.
Is that correct?
Yes. So it's
But
so to say, if
you would still use dominance to prove this.
Yeah. Because it does not require to repeat the entire proof for the other reduction. So maybe this was rather complicated. And for proving this the single fixing, you can just base it on a lexicographic comparison.
Mm-hmm. I see. Thanks. So, more questions, comments? So one question is, so maybe is, how do you have any sense of to what extent the mixed integer programming or OR community worries about these questions of correctness?
I think it depends a bit on the application. So there exist for sure instances where I would say people really want to have a true solution. So for instance, chip design, when a lot of money is involved for legal reasons. Um, so you don't want to produce, let's say, a computer chip, and you could upfront have decided, oh, there's a bug on the chip, the design is not fully correct, and then you need to replace it on all the machines. So therefore, sure, you want to have a true optimal solution. Whenever data is involved, I would say to a certain extent, people are interested in optimal solutions, but it's also a bit questionable because the data is also not necessarily correct. Maybe it's some forecast of future demand of customers and so on and so forth. So you don't have guarantee that that the solution will be realistic anyways. And then it also maybe doesn't really matter whether you have a true optimal solution or whether the solution is just good enough. So
Actually,
I think
that's
it
a very
depends on the
interesting point.
application.
Like, yeah, so if, I see. More questions or comments? So then I think let us thank Christopher again so much. Thank you.
Thanks for hosting me.